Hi everyone and welcome to your lesson on pipelining. I want to start off today's lesson with a quick sort of calculation that I want you to have a think about, and then we're going to go on to talk about how this links in with pipelining. Okay, so assuming you've got in your house one washing machine that takes 30 minutes to wash one load of washing, you've got a tumble dryer that takes 40 minutes to dry that load of washing, and you've got one folder, which in this case is my little Bitmoji, that takes 20 minutes to fold that load of washing. In total, it will take 90 minutes to wash, dry and fold one whole load of washing. Your task is to work out how long it takes to do 4 loads of washing. Okay, pause the video, have a little think about it, and then we'll come back and talk about it in a second. Okay, so today's focus is looking at pipelining. Okay, and this is the second part of your computer structure within the Advanced Higher Computing Science course. So you could have calculated this in two main ways, okay? The slow way would be if we think about the first load, the blue arrows representing 30 minutes for the washing machine, the orange arrows representing the 40 minutes for the tumble dryer, and then the purple arrow representing 20 minutes for the folding. It would take us 90 minutes in total to do one load, and then another 90 to do the second, another 90 to do the third, and another 90 to do the fourth. So in total, if we started at 6 a.m. in the morning, it would take us until 12 noon to stop the 4 loads of washing, which in total would take us 6 hours to do the 4 loads. But in real life, that's not how we would do it. Okay, what would happen is you would start off with your first load at 6 a.m. and then when you took that washing out of the washing machine to put it in your tumble dryer, you would also put your next load in the washing machine, okay, at that time. So you'd be able to start the next scenario. And then when your next set of washing was finished, you would move that washing to the tumble dryer, you would start folding the next one after you'd put on the next washing, and so on and so forth for the 4 loads. If you started at 6 a.m. and you continued this way, what would happen is you would finish at 9:30 a.m., which means that to get the 4 loads done, using simultaneous resources, it would only take you 3.5 hours. And this is how pipelining effectively works. Okay? What we can learn from this scenario is the following things. First of all, multiple tasks can operate simultaneously because they're using different resources. Because the washing machine is doing its task by itself, the tumble dryer is doing its task by itself, and the folding is happening by itself. If we ignore the kind of seconds and minutes it would take in between to actually do the loading and unloading, if we think of it as pure tasks separately, then this can all happen simultaneously. Pipelining doesn't help something called latency. Now, what latency means is how long the task takes in total, okay? Regardless of which way we've done it, whether you did it slow way or the quicker way, it still takes 90 minutes from start to finish for each load of washing to start from dirty to finish up folding and neat on the bed, ready to get going. Okay, but what it does do is helps with throughput. It improves the efficiency of your processor or the efficiency of the task with which you're doing, so that you can do multiple things at the same time to get things done faster in the long run. Okay, but each task still takes the same amount of time. Your pipeline rate is limited by your slowest pipeline stage. So in this case, what it means is because the tumble dryer takes 40 minutes, each kind of cycle, if you like, if you look at it up and down the way between, like, for example, here, the folding down to the washing machine, that still has to take 40 minutes. Okay, it still has to take 40 minutes regardless of how long the other things take, because it's the slowest stage. They're not all the same times. Okay, ideally the potential speed up you can get is equal to the number of pipeline stages. So in this case, we've got 3 pipeline stages: wash, dry, fold. Okay, effectively, rather than having everything happen in one go, because we're doing things side by side, you should be able to get up to 3 times faster. But there's a number of things that hinder this. One, we've already touched on already, is the unbalanced length of stages. So because we have something that's 40 minutes, 30 minutes, 20 minutes, what that means is there's going to be some dead time. So for example, if this was a real case scenario, me as the folder would have 20 minutes of folding, then 20 minutes to put my feet up and have a cup of tea while the tumble dryer finished, and I continued the scenario again. Okay, and that it leads to different parts of the computer system sitting waiting, not doing anything while longer tasks need to be done. So that doesn't really help with the speed up. Also, you need time to what's called fill and drain the pipeline. So at the beginning, okay, if you think of me as the folder, I'm not doing anything until we get into about 70 minutes into this scenario, because the washing machine is doing its thing, the tumble dryer is doing its thing, and I don't start folding until both of those things are completed. Okay, again, if we think of them as separate tasks and not me having to unload them and load them, etc. All right, so you need to fill this up at the beginning. Also at the end, the washing machine finishes working 70 minutes before that 3.5 hour period because it's finished its task. And that's what's called draining the pipeline system, so it stops again. If you have a continual system that runs 24 hours a day, then obviously this issue wouldn't happen, but it does in most real life scenarios. Okay, let's have a look at a slightly different analogy, just to look at some problems that you might come across. So in this analogy, we're talking about baking cakes, okay? The A represents 20 minutes that it takes to prep the cake, so that's all the mixing and the ingredients, measuring and that type of stuff. B is the 20 minutes of cooking, so putting it into the oven. C, in 3 blocks of 20 minutes, is your cooling time, and then D is your final 20 minutes that's used for icing, okay? So the whole thing for one cake takes 2 hours. So to bake 2 cakes, it takes 4 hours, or in minutes, it's 240 minutes. Okay, but there's no reason to wait to start the second cake. Okay, when we can pop it in, we start prepping it when we start putting the first one in the oven. So what effectively would happen with the pipelining is we would prep one cake, put that one in the oven, start prepping the second cake, put it in the oven, start prepping the next cake, and so on and so forth. Okay, in this scenario, if we look at only 2 cakes, over the whole time period, we actually save 100 minutes by pipelining our production process. Okay, nothing is being kind of used twice. Everything is working side by side. We've not got 2 ovens, we've not got anything fancy, but we can make use of the resources that we have there. But this can run into some problems when parts of your pipelining process require resources from the computer system. In this case, think about cake tins. Okay, if we only have one cake tin, we can't start prepping the second cake until after we've got the first cake tin out of the oven and the cake out of it to then start prepping the second. Okay, so if we have one cake tin that needs to be used by part A and B of the process, we can't then start the second cake until part A and part B are completed, which means that we start a little bit later. Okay, now still saves a lot of time, so we're still saving 80 minutes on the original. Okay, but it has an impact. So resources are also a really important thing to think about when we're talking about pipelining. And resources in the computer could be that 2 different parts of 2 different instructions need to both use the ALU or are both using a specific part of the control unit. Okay, so the computer has to make compensations for that, and that can also slow down the throughput of your computer system. Another problem you can have is where a problem occurs with an actual piece of code or something that you're running. In this case, for example, still sticking with the baking cakes analogy, maybe we bring a cake out in the oven and salt's been used instead of sugar, or maybe it's plain flour instead of self-raising flour. When we take the cake out of the oven at that B stage, because it's being cooked, we see that the ingredients were wrong, and what happens is the whole pipeline needs to be flushed. Okay, and this includes all of the different things that are being run. So we have to start number 1 and number 2 again. This is where our cake analogy kind of falls down, because once this one's out of the oven, it would be cool and fine. But in the computer system, everything has to be flushed and then it starts again, okay, which can slow down the process. So this works really well for sequential files if everything's working correctly, but not quite so well when you come across an error or something. Okay, let's talk about what this actually looks about with computers. Okay, so we already talked about in the last PowerPoint that instructions that we do are kind of split up into the fetching of them, the decoding, and the executing. There's obviously other considerations, perhaps when we're doing some saving and stuff, but just for this analogy, I'm going to talk about one instruction being fetch, decode, execute. Inside a computer system, if we were going to run instructions without pipelining, if we imagine this table to symbolize clock cycles, so 6 clock cycles, we would fetch, decode, execute, fetch, decode, execute. So to run those 2 instructions, it's taken us a total of 6 cycles. Okay, if we were to introduce using with pipelining, and we imagine that the fetch part is being used, let's just say that's the buses, the decode is happening within the control unit, and the execute is maybe a calculation in the ALU, each of those 3 processes are using different bits of the processor, okay? So once the buses have done the fetching for the first cycle, they can then start the fetching for the second cycle while the control unit is doing the decoding, okay? The control unit then starts doing the decoding for the second cycle, so the ALU can do the the executing, and so on and so forth. So we can actually complete 3 cycles in the lesser, sorry, 3 instructions in the lesser time of 5 cycles. So that's how pipelining can increase our throughput, and improve the efficiency of our computer system. Now, why would a pipeline need to be flushed? We already talked about the fact that if we had sequential order of items and then something comes across as an error or whatever, it doesn't really work, okay? With our washing and cooking analogies, both of them were sequential, so they followed the same set of instructions again and again and again. Now, pipelining is sometimes known as assembly line for this reason, where you're kind of going through the same instructions again and again, but that's not always the case, as we know, with computer systems, okay? When we come to computer systems and complex programs, quite a lot of the time what we do is we use conditional statements. So for example, we have 2 separate outcomes and we don't know what instruction we want to run next. And that's where pipelining can sometimes be halted a little bit, okay? Or we can create what's sometimes called a bubble or a stall because we're waiting for the next thing to happen. Okay, let's give you a quick example of what that looks like. So let's say we've got our first instruction, it runs okay. Our second instruction, it runs okay. Our third instruction, it runs okay. But what happens with that blue instruction is it's maybe like the end of a level in a game, okay? And when you get to that execute part, it's deciding whether or not it's going to load level 2. Now level 2 will be loaded if your score is over 10. So there's an if, there's a question, there's a condition that has to be met, okay? In which case, the pipeline or the kind of processor can't load the next instruction until it knows if it's correct or not. It might load what it thinks might be the case just to try and get a little bit ahead of itself, but then it might have to abandon the pipeline if it picked the wrong option. So what it would usually do is it would wait. Okay, if we get the score back and the score happens to be over 10, what would then happen is the next level would be loaded and then it would continue, so on and so forth. But you'll see there's this little bit of kind of dead time in the middle here where the processor has to wait to decide which instruction to encode next, which means that we've got a few clock cycles before the next instruction can actually be encoded and run, which makes the computer run a little bit slower. But these clock cycles, remember, are so so short that for humans that we wouldn't even really notice this delay. But it's to think about how efficiency in really fast computers and gaming and all the different instructions that are being run. Okay, remember the last thing I want to remind you of is that when we are talking about this throughput and we're talking about the efficiency of the computer, we're talking about a single core processor, a single core computer system and how the instructions are run within it. One thing that we can think about is if we started to introduce multi-core computer systems, each with those cores or those individual processors running their own set of pipelining inside them, starts to get a little bit like conception and you're running lots and lots of instructions inside computer systems. And that's how we start to build up the really fast and efficient computer systems that we're used to working with today. Hopefully that all makes sense. I've attached the appendix for you to have a little bit of read over and have a go of the quiz when you feel ready. Speak to you later, guys. Bye.